Hi everyone, thanks for joining us. I'm excited to announce our first speakers, Ehsan and Nishil, with their talk, Building Production-Grade End-to-End Encrypted Applications.
Yeah, hi everyone. Thank you so much for coming. We're like she said, our talk is called Building Production-Grade End-to-End Encrypted Applications. I'm Ehsan, this is Nishil. So I'm a senior engineer at Skiff, and Nishil is the director of security for Skiff. Just to give a brief background about what Skiff is, we're not going to talk too much about Skiff during the presentation, but we want to give a bit of a motivation for why we're speaking about this. Skiff is a privacy-first workspace, we say for the next generation of the internet, with end-to-end encryption built in by default. So what this looks like is we have a suite of products for workspace collaboration, Skiff Mail, which is an end-to-end encrypted email platform, Skiff Pages for document collaboration, real-time, Calendar, and then Drive, which is end-to-end encrypted file storage. And so you can imagine a lot of teams and businesses and individuals use Skiff to sort of work on their most sensitive research or projects. I lead the development of Skiff Mail and Skiff Calendar, and Nishil is director of security across the entire product suite. So to start, we'll talk a little bit about end-to-end encrypted applications and how they differ from traditional applications. So in a traditional application, let's take the example of like a traditional email service provider. Your email that you send, let's say to another friend, is going to be in plain text or can be decrypted by the server that is providing the service. So in a sense, we can say that the server, this email service provider, holds the keys to your email. And if the server is compromised, it's potentially possible for the contents of your email to be leaked. In an end-to-end encrypted application, data is encrypted everywhere and can only be decrypted by the user sending the email and the friend or the user receiving the email. So in a sense, the user holds the keys to their email. And on our service, all we see is a ciphertext, sort of encrypted, meaningless string of letters and numbers that cannot be reversed into the actual email content. So if the server is compromised, only that ciphertext is leaked. So overall, like, end-to-end encryption seems really cool, right? Like, it has all these privacy advantages. So why isn't every app end-to-end encrypted? And one answer for that is that it makes a lot of feature development and a lot of things you would do to build a really nice, compelling, easy-to-use product a lot harder. And why is it harder? It's because of this property we just talked about, which is that our service doesn't have the keys to the user's information. So a lot of different activities that would normally be pretty simple become much more complex because of this. Let's take account recovery, right? Like, let's say a user forgets their password when and is trying to log into their account. In a normal traditional application, you may just need to verify their identity, verify their email address in some way, and then you can just reset their password and give them access to the account. But an end-to-end encrypted model, that becomes a lot harder because we also have to help the user recover their keys, but we don't actually have access to that key as the service provider. Another sort of thing that becomes much more challenging is real-time collaboration. So in a traditional application, let's say multiple users are like typing on a document, you maybe just send all those different changes that they're making to a server. The server runs some algorithm to reconcile them and then can like distribute that back out to the users. But for end-to-end encrypted products, we don't know the actual changes users are making to these documents. So that becomes a lot more of a challenge. How do you reconcile changes? Maybe on the client. We'll talk about some strategies for that later. And then observability of product bugs. So there's a lot of really cool frameworks that you can install on your front end that will help you track when users are seeing errors and maybe a user can't click a button for some reason, or maybe users in a certain country are not able to load the site. But a lot of these will break end-to-end encryption because they'll send information about the user's page or the user's content that they're typing to the server. So in end-to-end encrypted applications, understanding what issues users are facing and solving those issues becomes a lot more challenging. And then there's many other challenges as well. So at Skiff, we believe really strongly in usable privacy, making privacy-first products that are as simple to use as their traditional alternatives. So a lot of what we'll talk about in this talk is how we've developed clever solutions to a lot of these problems that make the end user experience seamless, even if the application is end-to-end encrypted. With that, I'll turn it over to Nishil.
Awesome. Thanks, Ehsan, for that intro. So what I'm going to talk about here is we're going to go, in the theme of B-Sides is, putting the cyber in space. Or maybe it's the other way. I don't remember. But we're going to go through a mission. We're going to build an end-to-end encrypted mission log for our spaceship. And so what is one of the first things you're going to have to do when developing an application? Well, the captain's got to be able to log in. So let's just recap. Most applications, right, we have the captain would have typed their password in. The password would have been sent over the network to the server hashes that password, and then compares those hash values to authenticate the captain. Ultimately, this leaks the password to the server, but you're using it to hash. However, in end-to-end encrypted scheme, we might want to use that password to help generate the user's encryption keys. So that would imply that sending the password to the server would break the end-to-end encryption guarantees. So we can actually use a class of algorithms called an asymmetric or augmented PAG. You may have heard about this as the SRP, Secure Remote Password. Its more modernized version is called opaque. And SRP, just to provide a brief recap, allows us to authenticate the client to the server without needing to send the password. It also has a very strong benefit in being phishing resistant because the server also authenticates to the client. So here we have, passwords are not sent over the network, great, right? And we've mutually authenticated both server and client. And I'm just gonna take a tangent here, is that when reviewing kind of OWASP top 10, both the 2023 release candidate, 2021 also talking about these exact type of issues, there's really no mention of SRP, which has been around for 20 years, or opaque as potential solutions to password leakage problems in the industry. It's not even mentioned in the NIST standards. And so one of the things that I recommend looking at for most applications is actually adopting SRP or opaque as a way to prevent password leakage entirely in traditional applications. The way SRP works is, just to provide a really quick example, is it uses a Diffie-Hellman-like key exchange and a challenge response mechanism, but I won't go into that here. So if you get anything from this slide, from this presentation, is you can't leak passwords if you don't have them, right? And this has been a huge problem in the industry for many years. So the one thing we're heavily pushing for is traditional applications to adopt these sorts of mechanisms. All right, so now that rant is over, let's walk through how we can generate keys required for SRP to authenticate to the mission log server. We take our password and run it through Argon 2 ID, which some of you might be familiar with as a modern successor to PBK DF2, scrypt, bcrypt, all that fun stuff. We'll take it through Argon 2 ID, generate some random data. We'll take that random data and process it through another function called an HMAC key derivation function. And this basically just generates more random data. And from that, we can actually generate cryptographically secure keys. We'll generate 2 key pairs that we'll talk about in this presentation. We'll generate some signing keys, and we'll generate encryption keys. The signing key pair is actually used for the SRP protocol I mentioned earlier. And then the encryption key pair is actually what we'll use to bootstrap the end-to-end encrypted of the user data. Okay, great. But what happens when a forgetful captain forgets their password and wants to reset it? If the encryption keys are derived from the password, does this mean the captain loses all of their mission log data? So we'll talk about how we can go through a forgot password. Ultimately here, if we're thinking about the captain, their goal is to recover mission log data and change their password, right? Changing the password and losing their data would be a mission critical failure. The first step here, what we're gonna do, is to generate a new asymmetric key pair called the recovery key pair. And that's the key pair here in the middle black box. This recovery key pair is used to encrypt that user's asymmetric encryption keys I showed on the previous slide. This encrypted recovery payload is now stored on the mission log server, but can't be used to access the encryption keys, nor the mission log data. So now what do we do with this recovery key pair, right? We've encrypted this payload, what do we do with it? We can actually use Shamir secret sharing, split this private key material up into 3 shards, where 2 shards are needed to reconstruct the private keys. And what we can do is we can be clever about how we give these shards and how the user can access them. So for example, we can store one on the captain's device. We can store another one as a PDF document the captain hides underneath their bed. And a third we can actually store maybe on the server, because again, only 2 are needed to reconstruct the private key. And so by putting one on on the server, we can actually have the user go through traditional forgot password mechanisms. You can do email verification, you could do phone number verification, you could run any sort of advanced heuristics that we're already used to in traditional applications. But the point is, the captain needs 2 of the 3 to reconstruct their keys. So let's go through the actual process of resetting the password. The captain can present 2 of the 3 shards. We can reassemble that recovery private key, which is then used to decrypt that payload, the recovery key payload, which actually again gets them access to the decryption keys. So captain has their data. We can actually run a very similar process to gain access to the signing keys for SRP to reset their password. It's very much the exact same process. It's just a different key pair. So all of this complexity can be hidden within like the appropriate user flows. And so to the captain, they're just resetting their password. But all of this happens behind the scenes. Great. So now that we've talked about that, about how the captain can authenticate to the mission log, we'll talk about how the captain can actually use these keys to encrypt data.
Awesome. So our motivation for this section is now we know how a user authenticates, like the captain authenticates to their mission log, but we want to understand, okay, how does the actual end-to-end encryption process work? Like, let's say you wanted to upload a mission log and have it be end-to-end encrypted. How would you do that? So first, just to explain some really simple primitives that we'll use, there are 2 sort of classes of cryptographic algorithms that are going to be relevant to this discussion: asymmetric and symmetric encryption. So I'll start by explaining symmetric encryption. Symmetric encryption is a pretty simple class of cryptographic algorithms where you basically just have a key and you insert into this algorithm this key, or a passphrase, you can call it multiple things, plus plain text, and you get ciphertext. And then if you use that same key, that same passphrase plus ciphertext, you get plain text, right? So like imagine I was sending a package to Nishil and I didn't want it to be intercepted by anyone in between. I could put a lockbox in this package, right? And lock it with a combination lock, send that package to Nishil. And if I've told Nishil the combination before, like maybe I texted it to him or something else, he can use that same combination to open the lockbox and retrieve what was inside. Asymmetric encryption works a little differently. So in asymmetric encryption, you actually generate 2 keys, a public key and a private key. And then this is called a key pair. And this public key and private key are related through a special mathematical operation where the public key can be used to encrypt a piece of information that is only able to be decrypted by the private key. So the reason these are called public and private is because the idea is basically you can share your public key with the world. So in this case, Nishil could share his public key with me, post it on a public messaging board, whatever. And I can use that to, let's say, encrypt a letter for him in this case. But then only he can decrypt that letter with a private key. So the cool thing with asymmetric encryption is like I don't need to do this step that I mentioned before where like maybe I text the passphrase to him out of band. Instead, because there's 2 keys, I can just use his public key to encrypt something and he can decrypt it with a private key. So at Skiff, like Nishil was mentioning, and for most end-to-end encrypted applications, we assign each user an asymmetric key pair. So this is the public and private key. So let's go through encrypting the mission log. There's one more nuance. You might think, okay, so like asymmetric encryption is really cool. There's these 2 keys. You can post the public key. Like, what's the disadvantage of asymmetric encryption, right? And the disadvantage is because of the mathematical operations involved, asymmetric encryption is actually very slow for encrypting large amounts of data. Like let's say a file like the mission log. So symmetric encryption is fast, but it has this problem where you have to share the key in advance. So how do we combine these 2 things to encrypt our mission log properly? So what we'll do is we generate a symmetric key called the data key. This key is very small, like maybe 32 bytes, 32 characters. And we'll use the data key to encrypt the mission log with a symmetric cipher. This is very fast because a symmetric cipher is fast at encrypting large amounts of data. And then we use the user key pair to encrypt the data key itself. And this is also very fast because the data key is very small. It's only 32 bytes. And then we'll store two things. We'll store the encrypted data key, and we'll store the encrypted mission log. Now let's walk through how decryption works. So to decrypt, we'll use a user's key pair to decrypt this data key that's fast because the data key is small. And then we'll use the data key to decrypt the mission log. So you can see in this diagram right here, there's an encrypted data key with the user's key pair. We do decryption, we get the data key out, and then we use the data key with the encrypted mission log, and we'll get the plaintext mission log out. So now let's say I wanted to share this mission log with Nishil. So I've uploaded it, I've done all those operations. Now if I want to share the mission log with Nishil, all I have to do is encrypt that data key with Nishil's key pair as well and upload that to the server. Now Nishil can follow the same procedure to decrypt the document that I just described. One other really cool property of sharing a document in this way is notice that I did not need to re-encrypt the entire document a second time. I only needed to re-encrypt the data key. So it turns out this approach actually scales really, really well when you're sharing with a large number of collaborators, even as a further advantage than just an individual. So now let's say we have multiple mission log entries. I've uploaded it, I've shared the single mission log with Nishil, a bunch of time has passed, we've accumulated multiple of these mission logs, and we want to share a folder of these mission logs. And I want to share a folder with these mission logs without going, as opposed to going through this process of like sharing each one with him as I generate them. So one way to do this is to kind of treat folders like a user, where a folder is sort of a special construct that actually has its own asymmetric key pair. And when I add a log to a folder, instead of sharing it with a user, what I'm actually doing is I'm sharing the log's data key with the folder key pair. So now let's say I want to decrypt a file that is stored in a folder, a mission log that is stored in a folder. We kind of follow this tree hierarchy. So we have an example here on the right where there's a mission logs folder, in that there's a year one logs folder, and in that there's a 422 log for today. So what I'll do is I'll use my key to decrypt the mission log folder, and then I'll use the mission logs key to decrypt the year one logs folder, and then I'll use the year one logs key pair to decrypt the 422 log. So you might notice this is kind of following like a tree structure, right? Like a recursive structure for those of you that are familiar with like recursive algorithms. And indeed, this sort of forms this key system that we're describing kind of can be generalized to any tree where you have one root node that you are shared on and then want to decrypt any of the sub-elements of that node. So we just described a case of shared documents. At Skiff, we also are investigating using a similar approach for several other product features. So you can imagine that this would work well for a team inbox, like a user inbox or an inbox in email that multiple users have access to, or shared calendars that are popular in many other calendar softwares. So this is a calendar where multiple users can view and edit events. And I'll also just add that besides these use cases, these are some use cases that we have at Skiff, but you can imagine many other such use cases for what is essentially just a generic tree of end-to-end encrypted information. Can have applicability for a wide range of end-to-end encrypted applications. But a lot of folks here and a lot of folks around the world are not developing on end-to-end encrypted applications just yet. So we wanted to talk a little bit about how this can also be applicable to more traditional applications, right? So let's say you don't have an end-to-end encrypted, you don't have these keys on the client, but you still want to apply some of these principles. Let's take the example of you're storing a user's first name, right? Typically, when you're storing a user's first name, maybe you collect it on sign up, And then it goes through a bunch of different like data storage services, user authentication services, whatever, is ultimately stored in a database. And then later you want to read it all the way out, right? So you like retrieve it from the database, retrieve it through a user storage service, whatever. Eventually you display it on the user's page. But a lot of those intermediary services don't actually need to do anything with the user's first name. They're just kind of passing it on and passing it through. So one sort of principle you can borrow from what we just discussed is at the like sort of API layer, or the last service that needs to actually do a computation with the user's first name, you can encrypt this piece of information, right? And then when you're feeding it through all the dependent services, those services will just pass on this encrypted piece of data. And then on the other hand, when you're pulling it out, you can decrypt it at the layer that you need to access it. And what's really powerful about this is it means that now you've isolated the set of services that have access to the plain text copy of this user's name. And as a security engineer, you can spend a lot less time worried about hardening and like protecting the services that only have access to the encrypted copy, because you know that even if there was a compromise of those services, an attacker would only recover the ciphertext. And then on the other side, as an engineer who's working on these services, you can worry a lot less about a compromise of these services compromising the user's first name or any other piece of information that's encrypted in this way, because your application is only ever operating off the ciphertext. With that, I'll turn it over to Nishil to talk about how we can use this end-to-end encrypted context to enable many product features in different end-to-end encrypted applications.
Awesome. Thanks, Ehsan. So we talked a lot about data being read, data being written, sharing that data, but ultimately there's other things about data, right? Data schemas will change, data transmission layers will change. And so how do you adapt end-to-end encrypted applications for a lot of these future goals when you don't even have access to the underlying data? So basically everything about data except the data could change. And so how do we handle that? So let's talk about an example for like notifications. Let's say I want to send Ehsan a calendar invite to go over the mission log. I would encrypt a notification for Ehsan containing the event title and maybe the time. My phone sends that encrypted notification data to the server. The server delivers that encrypted notification to Ehsan's phone, or sorry, the other way around, to my phone. And then Ehsan's phone decrypts and displays the notification. So essentially what we've described is real-time unidirectional communication, right? And if you're not really on an end-to-end encrypted app, end-to-end encrypted notifications are actually very simple, can be supported by traditional applications. And the way you would do that is on device enrollment of accepting these push notifications from Apple or Google. You generate keys, and you send those keys to your server, and you would simply encrypt those notifications before sending them out. So this is really easy to set up. Don't need to have a full end-to-end encrypted applications, but you can send end-to-end encrypted notifications in traditional applications actually very simply. Great, what about bidirectional real-time communication? So we can actually use a data structure and algorithm called CRDT, conflict-free replicated data type. I won't go into that here in this talk, but the point is that CRDTs are eventually consistent, and I mean that in the computer science theory perspective, in that when collaborators are reading and writing from documents and generating these diffs are encrypted, distributed out to all the clients, and the clients are guaranteed to eventually see the same data. And so what we can support here is bidirectional end-to-end encrypted real-time communication. And so application encrypted live collaboration in traditional apps really only needs an ephemeral keys per collaboration device and per live collaboration session. So live collaboration for traditional applications can be pretty easily supported as well. And this also has the advantage of protecting user data from leaking into caches, often used to support live collaboration. Okay, so we talked about bidirectional, unidirectional real-time communication. What about data changes, right? Oftentimes your backend engineers will say well, this data schema doesn't work anymore. We need to make some updates. but you don't have access to the content. Not only do you not have access to the content, you have no control over when a client will come back online to actually perform the data upgrade, right? As a backend engineer, if I'm on my database, run a data migration, great, I can do that. But I can't tell a customer to come online and say, hey, we need your device to come online so we can run this data migration, so we can like support you in the future. That's just not acceptable. Imagine trying to call, if you're a consumer application trying to call 1 billion customers. It's just not going to work. So what we can do here is, for like the mission log example, we can maybe build like an initial version of this mission log. But let's say mission control wants to update the schema to clarify like the time is UTC, they want to add audio, recording the planet information, just like they're just trying to add things to it because, schemas change over time. And like, unfortunately, the captain and the crew have disappeared into a wormhole and we have no idea when they're going to come back. But mission control engineers are just like, well, we have to keep moving on, we have to keep building. And so they want to make sure we have both forwards and backwards compatibility. And actually, we take a lesson out from the SRE playbooks and infrastructure engineering, protobufs, which are often related to gRPC or internal service communication. And we can actually use protobufs to perform, to allow for this forwards and backwards compatibility. And so the way this happens is that protobufs actually will auto-generate code for serialization and deserialization. And you can say, like, why not just use JSON? It's been around for a while, supported everywhere. So you can imagine, like, if we're making so many different schema changes over time, you're going to have a bunch of these if statements or case switches about, version 1, this is the schema, version 2, this is the schema. And that requires humans getting it right. And we know how that can happen, especially over time. We're talking about years and years of data and data schema changes. What's the nice thing about protobuf is that it's self-documenting. You get exactly what you see, you know what fields are deprecated, and the serialization and deserialization is auto-generated by the protocol itself. So you never have to worry about your spec being out of date. It also has a nice advantage is that it's a binary serialization format, so it's a lot more efficient than JSON. But that's just a nice side advantage. Great. So another thing about building production-grade applications is your users or your engineers want to be able to debug and observe user behavior and be able to fix issues at the end of the day, right? Traditional client-side monitoring, like such as session replay or user monitoring, can leak user data or data about the user. So what can we do here, right? We can see an example of this is like some product that offers session monitoring, right? The user's clicking around, they're maybe adding products to a cart, they get angry, but ultimately you're recording the user session. And if we're doing that in an end-to-end encrypted application, though it may not break the actual underlying cryptographic guarantees, it really goes against the spirit of it. And so we're actually very, very interested in future work coming out of the IETF, known as the Distributed Aggregation Protocol. And at a high level, what this protocol allows you to do is send anonymized metrics to your server. And the way they're anonymized is that multiple users will have to report the same information, and once it hits a certain threshold, you'll get that data. So let's say you're seeing thousands of users run into an error, you'll still see that information, but you won't know anything about the end user, which is great. But right now, as we're still exploring this, like, we really rely on heavily pre-production testing, automated testing, and user error reports. Probably the same as many people here as well. So even this occurs actually in the security space as well. You say like, oh, haha, like bad front-end engineers, like you're recording user data. Actually, we have a problem with this in the security community as well. So if you look at content security policy trusted types, it's a fairly new policy beyond normal CSP. Trusted types was heavily pushed by Google and a few others to help protect against DOM-based XSS. And what this does is it looks for potentially unsanitized data landing into a bad sync. But great, I get this report, I'll find my DOM-based XSS, I can go solve these issues. The problem is that this starts leaking user data. And how does it do that? Well, because it's DOM-based XSS, the user input is part of the actual script sample that is sent back to your backend server. So you can actually see an example of this as we were testing this in our staging environment. If you look at the script sample towards the bottom right above the black box, you'll see DOM parser error, parse from string, and then you can see user data saying hey ya. So there's not even a way to turn this off. So really the solution we have is we can either look for DOM-based XSS and have this reporting enabled, or we literally have to fly blind like we've been doing for the last few years. And so this isn't a great example either. So it's not just to say that like we have issues in front-end tools. We actually have a problem with these privacy issues in the security community as well, in the AppSec community. So we talked a lot here about a lot of things, keys, a ton of work. What we hope to have accomplished here is clarifying a lot of misconceptions around the limitations of end-to-end encrypted applications, right? Authentication, password recovery, efficient data sharing, real-time communications over both unidirectional and bidirectional channels. We also talked about where it does actually get challenging from our experience, right? Data migrations, observability. But we hope that, if you're building more traditional applications, what hopefully you can take away from this talk and take back to your own organizations, is using SRP or opaque to prevent, password leakage and actually protect against phishing. You don't need to, buy into the hype of, hardware keys. They're great, they do their job, but we've had this protocol for, 20 years to deal with this issue. Application layer encryption at trust boundaries to prevent data leakage, though, it can happen at, people have talked about it a lot. We do think it's fairly powerful. And privacy preserving observability, like we talked about the distribution aggregation protocol coming out of the IETF to improve user privacy, doesn't require end-to-end encryption, but still allows you to collect this data in a more user-friendly and private way. With that being said, we just wanted to give a couple special shout-outs. Zach, who was at Skiff, he made a large amount of the crypto engineering contributions that we talked about here. Co-founders who built a lot, Andrew and Jason, who built a lot of the original implementations. Our entire team, we're a small team of 15 people. And we're presenting here today because of a lot of their work and contributions to what we've been able to do. And we are standing on the shoulders of giants, both like cryptographers, a lot of these protocols that have been built over the last 20 years. And obviously a shout out to all the BSides volunteers and organizers, because we wouldn't be here to be able to talk about this without them. Awesome. So we talked a lot. You might have questions. Happy to take those now. We have about 7 minutes for questions. So feel free to raise your hand and I'll try to see you in the light. Yeah.
You guys hear me? Good. I would ask a question about your sharing a file in a folder use case. So yeah, I would use. Yeah, for sure. For sure.
There we go.
Yeah, so I would use my key to decrypt that folder's key, right? And then I would use the folder key to encrypt the actual files, right? So that key makes it to my file, I use my key to upload files, right? So under what circumstances would you rotate that key? Like let's say you revoke my access to that folder. Would you rotate that key and decrypt all those files then, or what happens? Yeah, really good question. So yeah, I'll repeat the question. The question is sort of a clarification on how the folder sharing is working. Sort of asking like about how you use your user's key to get access to the folder. And then also let's say that the access was revoked. What sort of would you rotate? Yeah, so the way this will work, there's kind of a nuance here that we simplified for the purpose of the presentation, but I can explain it in more detail. So a folder kind of has this hybrid structure, at least at Skiff, where it kind of has this like asymmetric key pair where it almost acts like a user, which was the analogy I was making, but it also can sort of act like a document. So users can be shared on a folder. A folder actually has its own data key, and the data key exists alongside this asymmetric key pair that a folder has, where it can kind of act like a user and have documents underneath it. So that maybe answers like the first part of your question. Like that's how you kind of are shared as a user on a folder. And then the second part of the question was key rotation, right? So let's say a user is unshared from a folder, what ends up happening? So one really simple way to do this is to sort of re-encrypt the entire tree. That's not very efficient. So Nishil, do you know what our approach is? Yeah.
Yeah. So the what we're comparing here against is traditional applications, right? Versus in this context, key rotation. What we can actually do is just pretty much use server-side controls here, because what we can say is if the user is unshared on that document, we can simply say they no longer have access to the ciphertext. So though cryptographically there's an issue, ultimately if the user doesn't have access to that ciphertext, they don't have access to the plain text. And you could argue like, well, what if they have access to the old ciphertext? Well, that's no different than a user in a traditional application copying and pasting the doc somewhere else. So we really have to care about, can we protect the document against future changes? And that's the real question, or the confidentiality of that document for like with future changes. And so what we can do is apply server-side control and then look at like, okay, if we really need to re-encrypt this specific document, like allowing the user to do that. But in most cases, the server-side access control is sufficient.
Do you mind going to key generation?
Yeah.
Yeah, so my question is, I use a password and then I generate a signing and an encryption key, right? If I use a key,
No, there's a couple of salts and secret, like server-side secrets involved. To help. Sorry, not server-side, but yeah, there's salting involved and whatnot, so you won't.
client side, so the client has to remember.
So the salts are considered public. They don't need to be. You can't. So there's actually what 1Password does is they don't store the salt to make this brute forcing a lot harder. But technically, to keep the protocol secure, you can store the password in your own database, and the client can query it, and that's like perfectly acceptable. The salt.
Okay.
Yeah. The other thing that happens here is that what I didn't go into is that the SRP protocol also you can take into account the bootstrapping of that on the SRP protocol that actually prevents like the phishing. So even if a user typed in it's like their password somewhere else, assuming they weren't just capturing the password, which would break, that we can't do anything about, but if they were also running SRP on this phishing website, you couldn't use that same response to then log into like, Skiff, for example. So it does protect against that. What it doesn't protect against is like, yeah, the password leaked somewhere else and somebody typed it in again. Like, we're hosed either way. And so our comparison is always, do we have the equivalent security considerations in a traditional application, or do we exceed them, right? We should never be worse. So in some cases, we'll actually be equivalent, like the security model is no different, but what we're hoping is that in most cases, we're actually better.
Okay. I mean, because you said don't use physical FIDO2 keys, and I think they have better protection than all of this, right?
Yeah, so we offer MFA. MFA is possible, right? Because you could still basically don't respond on the SRP protocol until like the MFA challenge is completed. So you can still do MFA as much as you want. Like Skiff, we support WebAuthn. You can support all this key. So you can do all of that. Like none of that is prevented in these systems.
Oh, okay.
Yeah.
Yeah, you can just say it.
You just say it. Yeah, that's fine.
I'm curious, you have this authentication protocol. Is there any way to securely encrypt like an SSO or IDC?
Yeah, that's a great question. We haven't built that. It's something we're exploring. Oh, sorry. The question was, can this scheme be used to support SAML, SSO, kind of these other federated authenticated approaches? The answer is yes. We're looking into it, but we're really inspired by like what 1Password recently launched with their kind of federated identity, integrating with basically Okta, and that is they run a very, very similar authentication process to this, though maybe not exactly the same. And so we're pretty inspired that if they can support it on a 1Password with real enterprise customers using Okta, like there will be differences, but we think it's very possible. Like they've proven it out, so we're very optimistic that we could support that in the future. Yeah. Mm-hmm. Yeah. So you want to take the question? Yeah.
Yeah. So the question was, we're talking about the folder sharing again, and the question was, if we treat a folder like a user where it has its own key pair, are we sharing the private key with the users that have access to that folder? And the answer is yes. So the way it works is any user that is shared on that folder has access to the private key of the folder, and then they use that private key of the folder to decrypt any child documents. Yeah, so the follow-up was, what about in a situation where a user has access to the parent folder but does not have access to, we don't want them to have access to the child folder. So currently, cryptographically, that's not really possible to support, at least in our framework. You may be able to support that by server-side controls like Nishil was mentioning, where you could just not present the user the encrypted piece of information. But if they were it's not protected in like sort of an end-to-end encrypted context, right? Like if they did gain access to that ciphertext for that subfolder they're not supposed to have access to, or that subdocument they're not supposed to have access to, they would technically be able to decrypt it. We actually have a couple more minutes. I think we have till 12.
Yep.
So
Oh, we have to,
yeah.
Just speak.
Hey, thanks for the great talk. Have you put much thought into solving the problem of the user needing to trust the client-side software that you're serving them? Showing that you haven't been compelled or compromised into serving them something that undermines your controls?
Yeah, really great question. Nishil, you want to take that?
Yeah. Yeah, this is a tough one, right? Yeah. So the question is, basically, have we thought about the integrity of our client software, right? The client software used to generate these keys and encrypt and decrypt and all that. And it's tough because we don't really have a way to assure the integrity of the client besides hashing like all the scripts like through CSP and like assuring those like hashes are valid. Or so it's a little bit tough. We're thinking about it more, but we don't have a great solution to that. Like you could say like, oh, we can package it up into desktop apps and users can run it that way. So we're looking at stuff like that, but we're open to ideas. I know Cloudflare has been working on this with, I think they had a partnership with WhatsApp, if I remember correctly, to try to do better a client-side app, like to assure, I think what they did was like, when WhatsApp makes an update, then Cloudflare will look at like the hash of that update and make sure that it's like still valid. And so you kind of run into this like two-party computation scheme. I may be completely butchering that, so somebody can correct me. But that's something, I think that's like the closest we can get. Like we're just sort of reliant on, you know, what specs are coming out of web browsers at the end of the day. And the closest thing I've seen is like CSP and like hashing all the scripts and whatnot. And it's like, you know, you can do that, but obviously we always have like JavaScript dependencies. So it's like, okay, you know, it's turtles all the way down again, right? You're talking about supply chain issues here that we're not immune to, just like any other app. Like it's the same issues that you would have in both cases.
Thank you.
Yeah.
We have a question up top.
Oh, okay, great. Yeah, that's, the light is there. I can't see. You can talk. I probably can't. I can't see you though. That's okay.
There was a question on key rotation on the user keys, the key encryption keys. But if you have to rotate the key case, the data encryption keys, is it transparent to the users, or do they have to like have to reference log out, log in? Is that or does it work?
Yeah.
Actually, talk about the data encryption.
Yeah. So that. Yeah.
Another follow-up question. A feature that is non-existent today is the document when it is shared. Today we cannot share parts of the document. Are you guys exploring a feature where I have a 20-page strategy document where I want someone to have access to it, but only the 2 pages and be able to comment on it? So that means that I'll be using multiple keys to encrypt
Yeah, okay. I'll take those backwards. So the second question was around, is there a way to, if I have a document, of a very large document, to selectively share just parts of that document? From a cryptographic standpoint, I can't speak to product strategy, but I can say like it's very possible, right? All we're doing is just treating this one large document that the user looks at as one document, but treat it as multiple cryptographic documents, right? And so you can just compose that and say like, well, pages 1 through 10 is actually like one document, and 11 through 13 is a separately shared document, and then the rest is that. So it's like that you could just split up across multiple documents to support that. That would be fairly straightforward. You'd have to do a ton of work in the UX to make sure like it's pretty seamless for the user, but that's where the complications would be. And then the first question was around the rotation of the data encryption keys. So generally we try to avoid, in our application, to re-encrypt that data. Like we try to avoid it as much as possible, because the real issue becomes that if a user has like a huge document and they're re-encrypting, we have to have the client online, and users don't like to wait, right? Like they're just gonna close out the Chrome tab or the browser tab and leave, or they turn off their computer. Like users do all sorts of crazy things. And so we try to avoid those re-encryption operations as much as possible. There are cases where we will have to go re-encrypt, especially if the user is requesting it and whatnot. But for small documents, it's great. It's like super easy, you do it, it's fast, great. But even with symmetric keys, right? If I have like a zip file of like 2 gigs, right? I have to download that file, which is usually not too problem if you have a fast internet connection, re-encrypt, even with modern hardware. But the problem is you have to re-upload that payload. And so we try to avoid the re-encrypt operations as much as possible, right? And sort of say like, well, if the user doesn't have access to the ciphertext, we can actually deploy server-side controls to protect against it. And we can get around it. We can try to get around it that way in a lot of cases.
Just to add one thing, we left this out of the presentation, but a lot of these questions about the cryptography are really, really awesome to hear. Just wanted to plug that we actually have a white paper on our website that is sort of more of a technical paper, like almost like a research paper type thing, that you can go and read, and it spells out all of these operations and all of the sort of things that we do at Skiff to encrypt data in much more detail. It's just really simple. Link skiff.com/whitepaper. So if you want to read that after the talk, it goes into a lot more detail and like sort of math and cryptography detail on a lot of these things.
Yep.
How do you handle possible downgrade? Like if somebody
Oh.
sends you an email from a Gmail, right?
Okay.
Not encrypted, Gmail can't read your email. Like basically because of encrypting.
Yeah. Right, okay. So the question is, how do you deal with data coming into the system or out of the system that needs to be decrypted in order to have third-party interoperability, especially in the cases of email, for example, if you're sending a message from Skiff Mail to Gmail or the other way around. So actually what we do, what this slide was heavily inspired by what we do at Skiff. And in these cases, what we do is if a user is attempting to send to an external address that is not in Skiff systems, whether it's a skiff.com address or a custom domain, we actually have the user encrypt it with this special like encryption users keys or decryption users keys. And so this way we let the email go through as long as possible in our system, stays encrypted, and then only for the purposes of processing that and sending it out like via SMTP will we decrypt. And so and then we delete the plain text copies. We never store, right? And so this is one thing we also were hinting at here but didn't explicitly say, is that you don't we do as much as possible on these trust boundaries to say we're only going to process this data and we're not actually going to store it. And if we can, differentiate the storage and the processing of the plain text data, you can actually still reduce a lot of risk, because if you're storing all the data, that you can compromise whatever that data storage is and leak everything. But if you're processing it and that processing step is compromised, the only thing you can access is future data that is being processed in that pipeline, not all previous data. So you can actually do a lot of, you get a lot of risk mitigation this way too.
I have a follow-up. So are you working on a
Yeah, so we're looking at like supporting PGP. We were using more modern cipher schemes, but we think like, we have a lot of users that are PGP users. It's something we're exploring, haven't decided on. I'm just told I have to stop. So there's a ton of follow-up questions. I think there's a... Yeah, there's a hallway. Come meet us in the hallway. Like I look like a traffic cone, so come find me. It shouldn't be hard to find. So, all right, thanks everyone. And yeah, thanks for coming to the talk.